Hello. In this video, I'm going to go over the basic ideas when analyzing stress at a point. So, as you can see in this picture here, we have a rectangular cuboid, which is actually representing what's going on at a point, which has no size, so we don't really need to worry about dimensions of this cube. It's helpful to represent this as a cube because that allows us to use the Cartesian coordinate system, which we're all very familiar with. We can see here there's three main axes. It's a three-dimensional object. There's x, y, z. As far as the surface names go on here, you can see there's three different colors: green, blue, red. Green's associated with the positive x direction, red, positive y, blue, positive z. And of course, due to this view, there are three hidden surfaces in the background, and they are associated with the opposite directions of each of those axes. So, the opposite of the green here would be in negative x, somewhere back here. Then over here, there's negative y, and down here, there's negative z. And these surfaces are positioned in that the main axes are normal to them. They're perpendicular. So, the green is associated with positive x. Positive x-axis is the outward normal from green. It's the same with the other two, and also the hidden ones. So as far as the labeling system goes on these, you can see the two main symbols we use here is sigma for normal stress and tau for tangential stress. And as you can also see, there are two subscripts. The first one being labeling which surface it's acting on. So as you can see here, all of these top ones here, the first subscript is x, so they're all associated with the x surface, and then here they're all y and z. It's fairly straightforward. The second subscript defines the direction of which the stress is acting. So as sigma is normal stress, it has to be, normal to the surface. So sigma xx, you can see here it's on the x surface, and it has to be normal to this x surface. So it has to be moving in the x axis. So that's why it's x there. And tangential, it's the opposite of being normal. It's moving in the same plane as the surface. And there's two directions that can be in the same plane, y and z. So here we have tau yx. So that means it's on the red surface, but it's moving on that plane in the x-axis. And similarly here, tau zx, it's on the z surface and it's moving in the x-axis along that plane. Similar with these other two examples here, it's just swapping them around. Okay, so as far as directions go, the sign convention can get a little bit tricky because we have a lot of different axes around. We have positive x, positive y, and so on. And keeping this straight as far as what is actually positive and negative that you're working with, it can get a little bit tricky. So let's read through this quick. So on the positive x, y, and z surfaces, the stresses that will act along the positive coordinate are given a plus sign. The stresses that act along the negative coordinate are given a minus sign. However, on the negative x, y, and negative z surfaces, The stresses that act along the negative coordinate directions are then given a plus sign, and the stresses that act along the positive coordinate direction are given a negative sign. So kind of the thing to remember about this is that it's relative to what you consider moving in the direction of the surface. So I mean, it's like, so on the positive surfaces, when you're moving further positive, you know, you're moving further in their direction, then that's considered positive. And then when you're moving the opposite, it's negative. On these negative surfaces, moving in their direction, their positive, would be moving further into the negative, giving it a plus sign. It can be a little bit tricky, but just remember that it's relative to which is the positive for that surface, which is moving further into that direction. So on to plane stress. Now, when you're analyzing stress at a point, when you have a three-dimensional shape, basically it's too complicated. You have to move on to much more advanced methods of actually solving all of that at once. But with a plane stress, we have reduced it down to just two dimensions, x and y. And once you have it reduced down, you're able to solve these even with just hand calculations. And the way that you can actually reduce this down to a plane stress is basically everything in this z direction is 0. You may know this is done by using a free surface. Basically, let's say you have a beam and you want to look at stress on the point on the surface of this beam, and the surface would have the outward normal of the z-axis. Now, on this surface, there is no load applied. It's a free surface. That would mean in this z direction, there is absolutely nothing going on. So you can just say it's all 0, and the only things we need to consider are the other two directions, x and y. That's the core idea behind this. And from your other analyses, or either you're just given the information, you can write everything. You can apply all the information onto a plane stress square as shown. And from this, you can do further analysis. Now, one thing to note is that on this plane stress, everything is summing up to 0. You can see you have in the positive x direction, you have sigma xx. Negative x, you have the same amount. Same with the y, z, the net moments are 0. You can see the same amounts are coming to each other, canceling everything out. So really, the ultimate goal of analyzing a plane stress like this is to try and find the maximum amount of stress involved, so that you could design around, the maximum. It's the maximum that you're going to have to worry about the most. The problem with this is that when we apply these coordinate systems, the x, y, and z, we're really just orienting them in a way that makes sense to us. So, you would look at the beam and you go, okay, up, let's say that's y, and to the side is x, and everything. But it's really just kind of an arbitrary choice of where to place these axes. And because it's arbitrary, that doesn't mean that in these directions, these values you're finding are going to actually be the maximums. There's nothing saying that these are the values that you need to worry about the most. So that's where stress transformation comes in, or coordinate axes transformation comes in. And the goal of this is to find in which direction transformed from our original choice is the maximum value is going to be found at, and then you can calculate it. So here we have our original x and y axes, and we're going to apply a new set of axes, x1 and y1. These are also commonly referred to as n and t. We're going to apply these at a new angle, and you will be able to find different values as far as the stress is concerned. Now, one thing that you need to always be sure to do is that this angle between the axes is always going to be applied in a counterclockwise direction. And we're looking at this angle in terms of x to x1. You can see we have angle theta. X to y must always be 90 degrees. x1 to y1, or n to t, must always be 90 degrees. And it's this angle between the two x axes that is the transformation angle, and it's applied in a counterclockwise fashion. Okay, so these are the stress transformation equations that you can use to find out on these new axes what the stress is, the normal stress, the tangential stress, and so on. They're fairly simple. They just involve taking the values that you should already have, plug them in, and then put in all of these, it's 2 times the value of the angle that you're transforming it at. And you can see here we have a new plane stress square that will have these new values on, and it's just shown it's at a different angle as it was before. And an important observation here is that this equation here in the yellow, it's a check basically. Sigma x plus sigma y should equal sigma x1 plus sigma y1. So basically, the sum of the original normal stresses should equal the sum of the transformed normal stresses. So you can use that as a check, and once you do your calculations, if they don't add up, then you know that something's going wrong. You should recheck your values. So in the following videos, I'm going to be solving through some simple just stress transformation, just fairly simple stuff, and I'm going to show how you apply the MechMat program to help you solve these. And there are some issues sometimes in that the program only allows you to choose a theta of 0 to 90 degrees, and sometimes you are transforming it more than 90 degrees and you have to make a few changes. But I'll go over that in different videos, and these are just the basic ideas. These equations are really the main equations you need, and of course just be very careful to make sure that you are staying consistent in your sign convention.